Hey everybody, Doc C back again to give you your first installment of the lectures for Unit 1. And I'm starting here with kind of the materials page to show you, walk you through Unit 1, and then we'll talk about what's in Unit 1 and go through the information that you need to retain for the assessment. I think in an earlier video I went over the start here for Unit 1, and I think I also went over the study guide. So I'm going to skip down right here to the Unit 1 slideshow presentations. And I'm going to repeat myself probably a few times on this. In here, you're going to find all the information that you need for the unit. And got the slideshow presentation here right now. One of the things that's not here, because I'm recording it, is the Screencastify videos. You will have several of the Screencastify videos to watch in conjunction with the slideshow. So you can open up the slideshow and it will come up as a Google presentation. This is the slideshow presentation for Unit 1. All the units 1 through 8 will look similar to this. But I just want to go through a few things before we really get started on the notes, and that has to do with, sorry, as you can tell I got a bazillion windows open, that's kind of how I roll. I do encourage you that when you are watching, well, first of all, watch or / listen to these presentations. I've got a Chromebook, and because I've got a Chromebook, hopefully, yeah, I can write on my tablet. Yay! Yay, write on my tablet. Which is cool because it allows me to kind of use my tablet as a chalkboard or a bulletin board or whatever. I'm not speaking very well right now. I get too much summer vacation in my head. But point is that it isn't just audio. There'll be videos here as well. And explanations of what's going on with the slideshow. So please don't just read through the slideshow without watching these presentations. I am aware that they are long, and there may be days where you would really rather not do it, but it really is important that you listen to the lectures and not just read the notes. Without doing that, without listening to the lectures, you're going to probably miss about 60-70% of the information. So again, I encourage you to do that. Most of my students either take notes by printing out the slides or taking notes on a separate sheet of paper. This is, again, it's not a required thing. I'm not going to, ask you to show me your notes afterwards. But I might ask you if you do poorly on a test and you're like, well, I don't know how I did poorly on a test. First thing I'll say is, can I see your notes? Because looking at your notes and seeing what you're doing will help me understand where you're going wrong, where the trouble points are and what we can do about it. So, and if you're not taking notes, I'll say, well, that's probably the first thing you want to start doing. If you're printing out the actual slideshow, I know it took me a long time to figure this out. Until I got smarter and actually Googled it. There is a video, YouTube video, that directs you to a short tutorial on how to print out multiple slides on a sheet, so you don't get that huge one-page sheet or slide on a sheet, and that does help, obviously, to make sure that you don't waste a ton of paper. All right, I think then we can go back to the slideshow and we can go through some of the things that I want to talk about. I'm going to try and hit the highlights in these slideshows, the parts that are really most valuable and sometimes most difficult. So keep that in mind, and I'll reiterate that as we go through. Hold on, the dog alarm just went off. I'm recording this first lecture in my house, and Amazon just delivered a package, and the dog alarm went off. Oh, you can be quiet now, Amazon. Evidently, I talked too loud. Now Amazon is talking back to me. But anyway, I've got I've got 4 dogs actually, and because I have 4 dogs, and they are a little territorial when it comes to people dropping off packages, sometimes they will bark. So, and I also, you may hear a bird tweeting in the background. That's because I also have a lovebird. I'm not loving him right now because I wish he would be quiet. But anyway, we can talk about that later. So back to what we were talking about. So one of the things you will notice on this slideshow presentation is, let me go back down here to the third slide. You'll notice that the book cover is a sunflower. And right away you're probably like, oh my God, I don't have a book with a sunflower on it. I have a book with a other flower in it. I don't know what kind of flower that is. But you have a different edition. The sunflower book is the 11th. The blue book, blue flower book is the 12th. 12th just came out. I have access to it online, and I will be assigning things for you to do online as well. But I've gone through it, I've looked over it, and usually when they do these new editions, it's very little that they change. They'll change some of the page numbers around because they're adding different figures, and they'll add a little bit of new information, but for the bulk of it, the information is going to be the same. Okay, so don't freak out if you've got that sunflower book. Sorry, if you have the blue book versus the sunflower book. You're supposed to have the blue book. And if you have the sunflower book, perchance, that is also okay. Either one of those editions will work, because when I give assignments, I'm not going to give page numbers. I'm just going to give sections, so the sections will be the same. So I think that's what this next slide actually says. Yeah. Okay. As a general rule, you should be using the book as a reference. In the study guide, it says to read certain sections, but please know that we don't cover everything in the book. We probably cover about 85% of what's in the book, so it's a large percentage. But look at the lectures, because you only have to, and also the study guides, because if for example, in Unit 1, we're only going to talk very briefly about one section. That's it. Okay, you don't have to read all of Chapter 1. This is a long class. It has a lot of material. It's fast-paced. So I don't want you to spend time reading stuff that you don't need to know. Okay, so again, I strongly encourage you to take notes over the material as you read and listen. Studies have shown that if you write something down, it really helps to retain the information. If you don't, like within 24 hours, you lose, I think it's 60 or 70% of what you learned the day before. So within a 24-hour period, if you haven't written something down, you lose a huge amount. So I encourage you to do that. Okay, so Chapter 1 is on basically all the kind of introductory stuff that you might have seen in another course, maybe in a biology, honors biology, freshman year, sophomore year kind of thing. We're not going to talk too much about that, and I'm actually going to breeze through these pretty quickly. And the reason for that is you are going to do a lab in this unit on scientific observation. And basically, how do scientists observe animals in a natural setting, and how they collect data, and some of the basics of experimentation. We're going to run you through in a lab. So I'm going to jump down here to all these slides are regarding Jane Goodall, who studied chimpanzees in the wild, and all the research she did, and we really don't need to talk very much about that. So we're going to move down here to slide 8. In science, we have what's called a hypothesis, and a hypothesis is something that you make, an explanation that you make based upon the observations that you have made and some assumptions you're making as well. One of the key aspects of a hypothesis is it's testable, so you have to be able to test it. And what do you test it in? Well, you test it in an experiment. Okay, so a hypothesis is kind of a guess. And I know, depending on who you talk to, some people would say this isn't the best definition, but I like to say it's an educated guess. It's educated on your observations, and it's on your assumptions as well. But it's pretty tentative. You don't know for sure if it's true or not. Right. If you have any questions during this long thing, you can always write them down and message me, um, and I will get back to you. So, observation, why doesn't my desk lamp work? Now, that seems like a really lame um, example of really what's the scientific method. But it turns out that's pretty standard. We do this all the time. We use the scientific method outside of science all the time. So, observation, desk lamp isn't working. Question, why isn't it working? What's going on? So, you know, you don't actually form a hypothesis. Well, you do actually, but you don't think about in my head. I don't think, oh, I wonder. I have a hypothesis that maybe the reason it's not working. You don't do that. You just think, oh, well, maybe it's not screwed in, or maybe it's unplugged, or the bulb's burned out, or do I have any electricity in the house? Maybe it's everywhere. Okay. So you come up with all these suggestions or guesses, and then but all of these are testable. So I can go and check if I can turn on the light switch, or a light switch, or I can try the TV or other things. That could be the electricity. I can screw the bulb in again. I could check, take the bulb out, and see if it tinkles. If it tinkles, it means that the little filaments in there have broken, and that's the bulb is burned out, basically. But they're testable. That kind of leads you to this loop where you've got a hypothesis. Your hypothesis might be right, might be wrong, but it kind of you go through these steps and then go back to it. If the hypothesis is supported, then you try something else, like if its bulb is burnt out, and you do that tinkle, and yeah, now the filaments are moving. Now you can put a new bulb in there, and hopefully when you turn it on again, now it works. So your hypothesis is supported. Okay, so that's a simple example of a hypothesis that doesn't really have anything to do with science. Okay, so hypothesis has to be testable. For example, the hypothesis that ghosts fooled around with the desk lamp can't be tested. So I can't conjure up a ghost, or I don't think most people can anyway, and say, did you mess with the light bulb? Okay, that's not something I can test. So supernatural and religious explanations are something that science can't address. And so you will hear throughout this course, and you'll hear outside of this course as well, about how, in school we teach science, but and this will lead into evolution at one point, and I'll give you a long explanation of why we do science and not religion when we get to evolution. But long and the short of it is, you can't test God, for example. You can't test a ghost. I can't ask God to give me a miracle, and then ask God to give me a miracle for the next, 10 days because I need to replicate my data. That's just not something that science can do. It doesn't make religion wrong, and it does not make science right. But it's just something that we can't address. All right, so I'm not going to go through all these slides because I think they're fairly straightforward. If you've made it to AP Biology, you kind of understand scientific process already. So I do want to, actually I don't, now that I think about it. I'm not going to talk about this too much as well. You're going to do a laboratory investigation with roly-polies. Roly-polies are little isopod critters that live underneath rocks in dark places. You've probably seen them. The lab will talk more about that when you get to it. But you're going to do an experiment where you're going to test some hypotheses. You're going to use these words, and you're going to make hypotheses. You're going to perform a controlled experiment. And you will also be asked to talk about what the independent and the dependent variable are in that particular experiment. So I will leave most of that to the actual lab. Um, Theories. One of the things that we talk about in this course is the idea of a theory versus a hypothesis. So a hypothesis is it's pretty vague. It is testable, but it probably maybe 50% of the time, I guess, depending on how good your experimentation and your observations are, they may not be right. Hypotheses might not be right. Um, Theories, on the other hand, have been tested over and over and over again. So they have a large body of evidence, and they're usually considered pretty solid. I'll give you an example that we'll come back to later in the course, and that is gravity. Gravity, believe it or not, gravity is a theory. Nope. The reason it's a theory is because it explains a huge amount of things that occur in our world, right? You take a pen, let go of that pen, it's going to drop to the floor. That's pretty straightforward. Everybody believes in gravity. But it turns out that the law, it's not a law, actually, it's a theory, because gravity cannot predict how very small subatomic particles work, and it also can't predict how very large bodies like planets will move. Okay, it doesn't do a very good job on either of those things. So what that means is, for most things, the theory is solid and it leads to correct predictions. But there's a few things that still need to be tweaked with it. We still have to figure out some things to make gravity into what we would call like a law. So we've got some laws as well, especially in the physical world. But gravity is not one of them. It is only a theory. All right. Let's move on to chapter 2. Same thing is going to work for chapter 2. I'm going to go through some of these things, but I will not go through all of them. The slides that I do not go through are still important, and you should read through them, but it's the ones that are a little harder in concept that I'm going to spend some time on. Okay, so I know a lot of students who take AP Biology tend to freak out a little bit when I say, okay, we got to talk about chemistry. Some students have a great time in chemistry and love it, and others not so much. So this speech is more for the people who don't like chemistry than for those who do. Chemistry is the foundation of biology. When you take Tylenol, Tylenol is a chemical. It is a chemical compound made up of certain things that do certain things to our body. So we have to know how those chemicals interact with our body to know that they relieve pain, but also don't cause damage to our bodies. Okay, so we need to know about chemicals. When you think, there are neurotransmitters that are basically just chemicals that are being released from your body, from your brain, from the rest of your body, to send messages to other parts of your body. The way drugs work is they act upon those neurotransmitters. And so knowing the chemistry really helps us understand the biology. So it's something we do need to deal with. But once we get through chapter 2, we will apply our chemistry, but we won't be doing any straight up chemistry for the rest of the year. And that also includes, we're not going to do any, we're not going to do any orbitals. We won't do the SPF thing. I'm not going to make you memorize a periodic table or any of that stuff. Okay, so it's much more application in nature. So we do need to understand that while biology is the study of life, the reason our life exists is the fact that it can work within the laws of physics and chemistry. In a perfect world, we would actually teach physics first, then chemistry, and then biology last. But the reason we don't do it that way is because usually students don't have the math skills to understand the physics first. So it's usually taught biology, chemistry, and then physics. But to really understand biology at a very fundamental level, and I'm talking like PhD people, not you guys, it really is important for you to have some understanding of physics as well. Okay, here's an example of that. There's just some critters here. These are some ants, and they are using a chemical, formic acid. They're actually going doo doo doo. They're spitting it at the invader because those predators don't like the formic acid. So do need to know that, or do need to know chemicals. So what do we need to know? Well, first of all, CHON, carbon, hydrogen, oxygen, and nitrogen make up almost all of living matter. So those are the big ones. And when we get to macromolecules, we'll talk about how those chones are used to make those big macromolecules. There's also some smaller ones. And they're listed here. And you can see there, you don't ever have to remember percentages. I'm not going to ask, is it 96%? Is it 95%? Is it 94% that chones make up? Instead, I would just ask, what elements make up the majority of our body? But even that is a pretty basic question that I probably wouldn't ask. So we also have these kind of trace elements that are in very small amounts, but are also important. And we're going to talk about all of these as we go through the course: nitrogen, calcium, phosphate, or phosphorus, all the way down to magnesium. We'll talk about all those, but not. We don't have to worry about those percentages. All right. Carbon is used to build biological molecules like carbohydrates, proteins, lipids, and nucleic acids. And carbon is used as a storage compound and also for storage or for cell communication and cell formation. Nitrogen is used for proteins and nucleic acids. Phosphorus is used to build nucleic acids. These are all just examples of how these elements can be used to make particular macromolecules. And we'll talk a little more about macromolecules as we go on in the course. Okay, atom. You should at this point be familiar with an atom. An atom is the smallest unit of an element. And then within an atom, there are even smaller subatomic particles. But if you take a neutron away from, say, a carbon atom, it's no longer the same element. You've changed it. Okay, so there are 3 subatomic particles that we will talk about: electrons, protons, and neutrons. Neutrons don't have any charge. Protons have a positive one. Electrons have a negative one. I'm hoping at this point this is all review. Like I said, we're not going to spend a huge amount of time on this. And the chemistry that we're going to be doing is pretty basic. So hopefully that will help you out. Okay, so in the nucleus we have our neutrons and we have our protons. So here's our protons with a positive, and our neutrons, they don't have any charge on them, so I won't even put anything there. And then these are the electrons. The electrons are not in the nucleus, they're floating around the outside. Okay, and that is very important in terms of biology and living life. So if we go to the next slide here. I like to, hopefully you've played the game Tetherball. Tetherball is, my drawing skills are not the best, so I'm going to try this. But so you've got some type of base, and you got this pole. And off this pole you have a string or a rope, and tied to that is a ball. And one person is on one side. Here's my person. I can't draw. Sorry about that. And then I got another person on the opposite side. And the goal, this person's very happy. On cross-eyed too, evidently. Got a little hair. Okay, maybe not. The goal is to hit the ball in a way that allows it to wrap around the pole in your direction. So one person will hit it and try and go clockwise. The other person will hit it and try and go counterclockwise. Why am I talking about tetherball? I'm talking about it because tetherball, in a way, is kind of like electrons in an orbital floating around the nucleus. When you hit that tetherball, it's going to you're going to accelerate it. So it's going to have this force behind it. And the other guy on the other side, maybe he's cross-eyed because the other guy hit him already. I don't know. But it's got velocity associated with it. It has energy associated with it, is really all I'm trying to get across. So here, if I've got an electron and this little dude here, he hits the ball is like the electron, so I guess we can make that an electron there. Okay, the ball is like the electron, and when that guy hits it, it's going to go out in energy level. And if you think about it, if you hit a ball, it's going to go faster than if you just let it drop to the tether and drop to wrap around the pole. Okay, so electrons can absorb energy, and that makes them move faster, and that makes them have more energy, just like a tether ball when you hit a tether ball to try and wrap it around the pole. That's all I'm really trying to get at this point. So electrons can be energy carriers, and they can either become more energetic, so in the case if you hit the ball, or they can also drop down again. We can say now, okay, well, now we don't hit the ball anymore, we just let it fall back, let gravity do its thing, and now it's going to fall back down, and it's going to lose some of that energy. So electrons can gain energy, and electrons can lose energy. That's really the long and the short of it. That's all I'm trying to get across right now. All right. How an atom, how an element is going to react is going to be based on how many electrons there are in different shells. And so we can look at periodic table and we can look at the distribution of those elements. Like I said, we're not going to focus on that in here too much. We're going to talk a little bit about what are called valence electrons. And valence electrons are the ones that are found in the outermost shell of the atom. And these specifically are the ones that will determine whether or not an element is reactive or not. Elements that have a full number of valence electrons are said to be chemically inert. In other words, they do not want to react with anything. So example of that would be a neon gas, any of the noble gases. So such as neon, right? And the neon signs. These guys do not like to react with anything. But there's other things that are pretty chemically inert too. So for example, CH4. CH4 is methane. Methane is also fairly chemically reactive. Chemically unreactive, inert. Okay, and in our body, the reason that we don't spontaneously combust is because these elements have combined in a way that produces a situation where all of them are chemically inert. They do not want to give up electrons or take in electrons. Okay, where this starts to become important is when we talk about bonds. And before I go forward, I'm just going to ask you a question. I'm going to see if you can figure out, or not figure out, if you can remember from your chemistry any types of bonds that you remember. Okay, so take a second and first of all think about what a chemical bond is, and think about chemical bonds that you may have seen in the past. I'm going to just take a few seconds here and let you think about that. I'm going to eat my banana. No cheating looking ahead, by the way. Okay. If we go on to the next slide. Oh, wrong way. There we go. So chemical bonds happen because of elements, atoms of particular elements that don't have full valence electrons. So because they don't have full shells, they try to combine with other atoms, either the same type of element or a different type of element, in order to become chemically inert. Okay, they want to be what I call, with my freshmen, I call happy. Okay, they want to have a full valence shell, And if they don't have that, they will become chemically reactive, and eventually they will form a bond, a connection with one or more atoms to do that. So I asked you what kind of bonds you might remember. The ones we are going to talk about are covalent and ionic, and there's a few others that you probably haven't heard of, like disulfide bonds and hydrogen bonds that we'll talk about a little bit later. But to begin with, let's just talk about covalent, which is probably one of the most common ones that you may have come across. Covalent bond is when you share a pair of valence electrons, and the shared electrons count towards each, even though they're sharing it, they're going to both count towards that full outer shell for that particular atom. So let me see if I can give you an example here. Well, maybe not. I will in a second. Yeah. Okay. So if you're sharing one pair of one pair of electrons, they're called single bonds. So that would be a single covalent bond. If it's a double bond, it's two pairs, and then the other one that you can have that's actually not listed on here is you can also have a triple bond, which, as you might guess, is three pairs of electrons. So 3 pairs of electrons. Okay. Oftentimes you will see that bond represented by a line in between them. So if I have H, and then I have this line here, and I have another H, that is also saying that I have two hydrogens together. Okay, so that would be would actually be a molecule of hydrogen gas. Next page actually shows you some very common ones that you see in biology. First one here is the H1 that we've already seen. And let's see if I can blow this up. I don't know if I can do this on my... Doesn't look like it. Let's look at the hydrogen. Each hydrogen atom has one electron. And when you put them together, now they have two. And those two together are considered, now I have a full set of valence electrons for hydrogen. You're not going to be asked to say, does this have a full shell or not? That's way beyond what we want to do in here. That would be a chemistry thing for any of these. If you remember from your chemistry, you know that hydrogen only has one shell and it needs two in the outer orbital. So if you put these two together, then both those hydrogen atoms are happy, or they are stable. For oxygen here, it's actually 8 in their outer shell. And oxygen in its outer, they want 8 in their outer shell, but each one of these only has 6 electrons. So if you look in the middle, they're sharing 1, 2, 3, 4 electrons, which is 2 pairs. Okay, so that means that oxygen is this. Okay. Another one that you see commonly is water. We'll talk more about that later. And methane. For some reason, they don't have nitrogen on here, but nitrogen, that's the formula for nitrogen, or N2. And that is because nitrogen is sharing 3 pairs of electrons. Okay. In terms of stability, the single bond is always going to be less than the double bond, and that's going to be less than the triple bond. So triple bonds are going to be the strongest, followed by double, followed by single. Okay. This next concept is something we're only going to kind of touch briefly on, but it is an important thing to have in the back of your head because it has to do with a very important type of covalent bond. And I think I might call this a wrap right here because I think this is enough information for you all to digest right now. And then I'll come back in my next video and I will talk about the different types of covalent bonds you can have. Okay, so now that you have gone over this information, please go to the study guide. And in fact, if you want to, you can be doing the study guide by stopping the PowerPoint present, or by stopping the video and doing it as you listen to the video. That's totally legit as well. Please don't wait till the last minute to take that to do that study guide, because it will bite you pretty hard in the butt. So if we go back here into Unit 1, come on, study guide. Oh, evidently I haven't put it up there yet. Okay, let me show you that here in a second, if I can find the actual link. Which one is it? Maybe that one. There it is. Okay. So today we went through Unit 1, Chapter 1, but only talked about Section 3. And it's asking you to do this for that first chapter. And then we got up to, sorry about that, did it again. We got up to today pretty much here. Okay. So for this first lecture, I would, before I went on and listened to any more, I would make sure that I had gone through all of these pieces of information. Now, some of this information may not have been covered directly in the lecture, and that's why you also need to read over the sections. Okay. So whenever I can, I'll tell you to skip stuff. You don't need to do electron orbitals, for example. I told you we're not going to do Bohr models, so you won't have to do that. Okay. So before you go to the next lecture, please make sure that you have read over and done the study guide up to and including this section here on the nature of atoms. Okay. So go that far. And then when you're done, you can come back and we will continue.